Without further ado, we will introduce our moderator for today, Dr. Eric Rowe. Dr. Rowe is the Assistant Dean for Continuing Education in the Cockrell School of Engineering, as well as the Executive Director of Texas Engineering Executive Education, which is the continuing and professional education provider of the Cockrell School of Engineering. Take it away, Dr. Rowe.
Hey, thank you, Javier. Welcome to our webinar. In these Tech Talks, we look to share exciting and industry-relevant topics happening here at UT Austin and the Cockrell School of Engineering. We hope to bring you both cutting-edge faculty research updates and informed perspectives of our industry experts. If this is the first time you're joining a Tech Talk, the format is the following. I'll introduce our speaker. He'll present for about 40 minutes. As Javier mentioned, as you think of them, please type your questions in the Q&A window on the right of your screen. At the end of the Tech Talk, we'll leave time to address your questions. Our speaker today, Dr. Michael Perch, is an associate professor in the Hildebrandt Department of Petroleum and Geosystems Engineering. He's a well-regarded expert in reservoir characterization and modeling. Michael is relatively new to UT Austin, having spent 13 years in industry prior to bringing his expertise to us. Dr. Perch's research group works on reservoir modeling, improved data integration, machine learning, big data analytics, optimal decision-making in the presence of uncertainty. Michael is dedicated to professional development, as evidenced by both his resources posted on YouTube and, fortunately for our executive education team, his participation in the creation of our new Petroleum Engineering Graduate Certificate and Data Analytics. During this Tech Talk, Dr. Perch is going to focus on his research group's work on data analytics and machine learning for energy, geosciences, and engineering. I'm looking very forward to it. With all the work we've been doing in the energy sector, I can't think of a more salient, relevant topic right now. So, Michael, thank you very much for sharing your work today and handing off to you.
Thank you very much, Dr. Rowe. I do appreciate that introduction, and I do appreciate the opportunity to be able to share some thoughts with you guys, with all of you today. Now I'll go ahead and share my slide deck so you can all see it. There we go. Do you all see my slides? All right, thank you. I appreciate that. So I appreciate the introduction. I'll just comment on the fact that it is my pleasure to be here at the University of Texas at Austin. I have had quite a few years of experience in industry, and I'm really very much enjoying my time and the welcome that I've had here on the 40 acres. Now, I should say that there is kind of a motivation for giving this talk today. And that is, I would really like to promote the idea of the new graduate certificate in the Cockrell School of Engineering, specifically Petroleum Engineering, Data Analytics, and a graduate certificate. Now, what I should say about it is that it's an opportunity for working professionals to gain important essential skills in digital. I will be conducting two of the courses, an introduction to geostatistics and data analytics and subsurface machine learning. And I work with Dr. Foster, also a professor in the Cockrell School of Engineering, and he covers an important course on high performance computing for engineers. And put all together, I believe it does offer an excellent opportunity for working professionals. And during this talk, I'll kind of hit back on this a couple more times and reinforce this idea. Now, every professor knows that we do stand on the shoulders of great students. So as I do show examples today from in the area of digital technologies for the subsurface, I will be relying on the work of many of my PhD students. I have a great team of 13 PhD students, and here's a list of some of the students whose work will be shown. And I do collaborate widely across campus, and so I want to recognize the faculty who co-supervise those students, and I just really appreciate the collaboration and the partnerships. So what's the motivation for sharing this topic today? What I would say is that energy needs new capabilities and solutions to fully realize value in the digital revolution. We need unique skill sets. We need new skills for engineers who have great domain expertise in the subsurface, and we are here to help you, to support you, to teach those skills. I think that's the main motivation here. Now, what I'm going to do is I'll cover just kind of a short introduction. I like doing that beyond the bio because it does give you a sense of where I'm coming from, how I communicate, and furthermore my motivations very quickly. I promise only a couple slides of, I hope it doesn't seem like bragging. And then I will cover the fundamental philosophy, my philosophy on subsurface data analytics and machine learning and its importance in the future. And then after that, we're going to go off the rails. We're going to talk about really interesting new opportunities and step changes in the way we get the job done with digital technologies, how engineers can work very differently, more efficiently, have more impact with digital technologies. So we'll show some of those methodologies. First, about myself. If you haven't met me in person before, my name does look a little bit difficult to pronounce. Just say it like perch. If you say it like that, and in fact, you say it as well as I say it, and after 100 years in Canada, my family has kind of forgotten how to pronounce our own name. I've been reminded by Ukrainians when I've met them. I have practical experience, so about 17 years of experience in consulting, teaching, in industry before I came here. In fact, I was leading a large research program. I was reviewing projects all over the world, and I came here to teach at UT. I did leave industry really with the attitude of giving back, sharing what I'd learned, having an opportunity to teach. And I do enjoy very much working in industry, consulting and connecting with industry quite a bit while I teach here at the University of Texas at Austin. As Dr. Rowe mentioned, I am active on social media and outreach. If you wonder how I teach, how I share information, there's no mystery. We can demystify that for you immediately. Go to my YouTube channel and you'll see how I teach, how I conduct lectures, and how I bridge the divide to help engineers gain new skills in the digital technologies. Go to my GitHub account. First of all, if you have a GitHub account, congratulations. That's cool. You've taken a major step in the digital transformation. I love to see that working professionals contributing to open source code development. If you go to my GitHub account, you'll find many, many well-documented, worked out examples, demonstrations, educational tools, and products. So you'll see how I teach and how I do hands-on experiential learning with new digital technologies. It's all there for anyone to see. Now, every time when you're a professor, you need to promote your groups, because I feel like as a professor, it's almost like I go to everything with my hat in my hand. And so I have 13 PhD students, a brand new consortium. I really do enjoy the opportunity to work over in the natural sciences in the area of a freshman research initiative and inventors program. And I do have a consortium too. So there's a lot of students I'm working with. Here's a little bit of information about my consortium with Dr. Foster, who I mentioned before, and also in partnership with Dr. Torres Verdin and Dr. Van Oort also. So if anyone's interested in this, of course, just contact me. I'm easy to contact, easy to find. All right, thank you. All right, I hope that wasn't too shameless. I think it was more than the couple of slides that I promised. Let's motivate. Let's really dive in and talk about what subsurface data analytics and machine learning are. We'll get down to fundamental definitions, and then we'll kind of have a shared sense about it from which we can go off the rails, as I promised, and look at some really cool opportunities, step changes. First of all, if no one has ever welcomed you to the fourth paradigm of scientific discovery, it is my great honor to do so. Did you know? Did you notice? We're in the fourth paradigm of scientific discovery now. Now, if you look at the previous paradigms, we've heard about this. The first paradigm, empirical sciences, you can go back to the days of the Egyptians and antiquity, and you can see all kinds of interesting experiments. Of course, they were learning by experiments and observing their natural surroundings. Second paradigm, the idea of theoretical science. We could find the classical laws, fit the equations, understand things at a deeper level. The third paradigm, well, I work in the world of heterogeneity. I understand this. It turned out that theoretical science could only get us so far. There's so many natural systems that are just heterogeneous, complicated geometries. At times we have to put it in a computer using knowledge from the first and second paradigm combined in the third paradigm to do computer simulation. And of course, the fourth paradigm, this is the idea of data-driven science. It's very interesting. We're living in a day and age where we're swimming in data, and we're recognizing that there's an opportunity to work with a data-driven perspective. That is, we're looking through large, big, varied data sets, and we're detecting patterns. We're learning new things by doing that. And of course, we get into topics such as machine learning, artificial intelligence, and so forth. That's the fourth paradigm of science, discovery. Now, if you're looking at that and you're thinking, wow, that's interesting, this is having a big impact, I would agree with you. It's having a huge impact everywhere. In fact, Deloitte did a study just a couple of years ago, and they looked across all sectors of our economy, and what they identified was the level of digital readiness for different sectors. And what was fascinating was that energy was somewhere in the middle. It was not tech, media, telecom, which of course was kind of on the leading edge with a high proportion of organizations with higher maturity. And it wasn't life sciences and healthcare, which was trailing on the other side. We're somehow in the middle of the pack. So all of the technologies and areas that I'll talk about now, we're seen as being in the middle, but at the same time, that means there's tons of greenfield opportunity and lots of interest around this. In fact, I visit many companies, energy companies, and every one that I visit is currently working on the challenge of digital transformations and how to find value with new digital technology. Now, I have biases. I do study probability and statistics, so I should just state my biases up front. And so whenever I'm asked to sit on a panel, this was an example of PricewaterhouseCoopers, and I was standing in front of or sitting in front of many executives from the energy industry. This is what I say. There's opportunities to do more with our data. In fact, I say the P10, the low case outcome for us would be we just use our data better, which I think will happen, and we're learning more that way. Opportunities to teach data analytics and statistical machine learning methods to engineers and geoscientists to improve their capabilities. And I will repeat myself, I'll come back to that. Geoscience and engineering knowledge and expertise does remain core to our business. So those are my biases. They're not just, they're well thought out. They're based on experience. And I'll talk more about that. Now, let me just make a couple of comments, because often what we see is people say it's the fourth paradigm of scientific discovery. We can throw away the old. Now, of course, we know that's not true. Anybody who works in the area of theoretical science knows that it's actually built upon the first paradigm. It's all based on experimentation, empirical science, and anyone who works in computational science with simulation knows that there's a mixture, empirical and theoretical components in these models. Just take the example of entrainment of grains within a flow. It's very difficult to try to figure that out from first principles, but you can do flume experiments and you can observe the rates directly and plot that. Yeah, so we need to augment with new scientific paradigms. That's what we do. We build with new ways to discover about the world around us. We don't replace the older paradigms. It doesn't happen. So let's keep that in mind. Big data. Are you working with big data? I already made the comment that we're swimming in data nowadays. We have a lot of data to deal with. This is really interesting to me, because if you look up the definition for big data, you can see an objective criteria. Do you work with big data? And it's all about the V's. The criteria are all V's: volume, velocity, variety, variability, veracity. Now, volume is interesting. It means many data samples, difficult to handle, visualize. I've gone to tech meetups and they say if your data fits on your hard drive, it doesn't count. I don't feel that way. I feel if it's difficult to handle, visualize, work with, understand its high dimensionality, I think that's volume. And you can check that box. You have this criteria met as far as big data. Velocity, high rate of collection. The tech industry often expects it to be real-time data. What I like to say for us in the subsurface, continuous relative to the decision-making cycles. Anybody working in the subsurface knows that we're constantly challenged, that we're constantly trying to make a big decision. We're constantly trying to apply some type of new processing or analysis while new data comes along. It's always challenging us to continuously update. Our complexity of our workflows suggest that even though we don't have real-time data often, and we do in smart fields, we do have velocity. And I give us full grades for that too. Variety, data from various sources with various types and scales. In fact, I say we win in that. We go all the way from pore scale, and I'll show you pore scale modeling, to basin scale, the size of entire basins. And imagine that the various sources and scales and types of data we work with are just amazing. Variability, data acquisition changes over time of a project. Anybody who works in seismic has seen this. Exploration, two-dimensional seismic, 3D, reprocess the 3D seismic, put some ocean bottom nodes in, and you're working with 4D seismic. They're all seismic, but the method of acquisition changed, and we have to integrate that. Check that box too. Veracity, data has various levels of accuracy. Actually, when I teach subsurface data analytics, I challenge my students, find me a source, a data type from the subsurface that has certainty, that does not have uncertainty. And we can't find one. No, all of our data has uncertainty. So definitely check that box. What I like to say, and this is why I spent a little extra time on this, subsurface has been big data long before tech even learned about big data, which means we're pretty good at it. We have a lot of great skills and technologies when it comes to working with big data, and we can harness that and we can build from that. I think that's a very important message. Now, I think this is also a very important message for those working the subsurface. The subsurface is unique. It's different and needs new skills, new solutions, not just the products off the shelf. Sparse, uncertain data, complicated, heterogeneous open earth systems. Very, very difficult to work with. I tell my students in my classes, we often sample directly 1/1,000,000th of the subsurface volumetrically speaking. Imagine that, and now we have to make major decisions. A high degree of necessary geoscience and engineering interpretation and physics. All of our data has a thick layer, irreducible layer of engineering, physics, geoscience interpretation. Expensive, high-value decisions that must be supported. Now, what I like to do is I like to compare and contrast this uniqueness of subsurface data analytics and machine learning with a common application of machine learning known as the recommender system. This is my Spotify account. It's a little bit dated now. My tastes have changed, but this was the summer of 2019. Now, if you look across there, you're going to see immediately that I'm Canadian. I like a bit of Canadian music, of course. And what will happen once in a while is this recommender system will get it completely wrong. And I hope you believe me, it really is getting it wrong. It will recommend Nickelback. Now, I want to just make the statement that I don't like Nickelback. That is a case of the machine getting it completely wrong. What's the cost of that? What's my response? Well, I start tapping my foot, I bob my head. You know, Nickelback is kind of catchy, but then I go, oh, it's Nickelback, and I fast forward it. There was no cost to getting that decision completely wrong. That is completely different than what we're talking about in the subsurface. They see every click, they see every song I listen to, they have all that information, and there is no engineering physics behind my music tastes. I don't think there is. We need to develop unique subsurface data analytics and machine learning solutions that integrate geoscience and engineering knowledge. That's for sure. It's not a recommender engine like on Spotify. Now we got to build up from fundamental ideas of statistics and probability. Data analytics is, in fact, the robust application of statistics to support decision making. I tell my students, if what you do does not impact the decision, you do not add value. Data-driven approaches are based on sound understanding of probability and statistics. We have to spend time developing that. When I teach machine learning, my students are always surprised that we get through probably a third of the course before we start building any machines. Inference and prediction with fundamental scientific and engineering approaches, that's what we need. We must build from probability and statistics using our scientific and engineering foundations. Now, how do I prove that to you? Well, the proof is in the definition. Look up machine learning, Google search it. You'll go to the Wikipedia page. Don't worry, don't be shy about it. Everybody does it. You go there and you start to read the definition. This is what you're going to get. It's fascinating. It's a study of algorithms and mathematical models. It's a toolkit. It's a bunch of models learning progressively, improve their performance on a specific task. Okay, learning toolkit. They're going to use sample data known as training data. Okay, learning from training data, that's nice, in order to make predictions and decisions without being explicitly programmed to perform that task. They're general. You make a machine that can solve one problem, it can solve another problem, it can learn the system. That's very, very cool. Okay, but most people stop there. If you read to the end of the article, this is what you're going to find. Where it is infeasible to develop an algorithm of specific instructions for performing the task. What does that mean? If you understand the engineering, physics, you understand the geoscience processes and relationships, and its physics too, you're better off to use that. Okay, let's be careful. In fact, I like to quote Professor Torres Verdin in our department, who in a PhD proposal defense said, we can't use machine learning as a crutch to avoid learning the deeper natural system. And I appreciate that. I think that's a really good comment. What about the data scientist? Everywhere you go, you hear the term data scientist, data scientist. I've worked in the subsurface resource industry for 13 years, as Dr. Rowe mentioned, and 3 years in University of Texas at Austin. I've taught many working professionals. I think it's 1,700 just last year alone in 44 different engagements. What I have found through my experience and documented by the responses that I get from these working professionals is that engineers and geoscientists are exceptional at learning new skills in statistics and in coding, and that the domain expertise remains the most critical piece to build from. And so what I'm finding is that engineers and geoscientists are well positioned to move into this space and to add value immediately in the digital revolution. Actually very exciting. Okay, I hope you're motivated. Now, as I promised, I'll spend the remaining time just it's kind of a rapid fire technical show of ways that digital technologies can add value. Subsurface, data analytics, and machine learning examples. I will give credit to the PhD students from the University of Texas at Austin, Cockrell School of Engineering, who conducted the work, and the other faculty. I want to show a set of new powerful tools, new ways for engineers to add value. Now, what's the motivation is I want to show you how much of a step change we should expect and how important it will be to have skills to understand so we don't run these technologies as a black box. None of them should be. We should be using our engineering geoscience knowledge. Okay, let's talk about machine learning to assist with data interpretation. I already said it. We have big data. In fact, all of our data has veracity issues. It's all uncertain. So let's talk about how we aid the interpretation of these uncertain data sources. First of all, it doesn't matter what type of application you have in the subsurface, fluid flow is important. Groundwater, contaminant mitigation, carbon dioxide sequestration, oil and gas recovery. All of these methods, we're concerned about what goes in and what comes back out, even geothermal. And so we need models that allow us to look through large, complicated spatial data sets and tell us about what is communicating with what. What did we inject here and how do we partition it to different locations where it's produced? It's very, very important. Now, a popular way to do that is based on working with a methodology for matching signals. It's known as dynamic time warping. What we've been doing is we've been working at enforcing physics, engineering physics into dynamic time warping. This is fascinating. We have one signal of what's being injected into the ground. We have another signal of what's being produced from the ground. And we can use engineering concepts, our knowledge of flow, to impose constraints such that when we map across these signals, we're able to see how the fluids are flowing through time and space. We do it in a way that we honor our knowledge about the physical system. This is fascinating. It's a great opportunity to reduce the uncertainty models, and it's a highly visual method. It aids interpretation, which always is a great idea, to have a methodology we can diagnose. Now, we also have to work with large sets of well logs, many different logs that we're measuring at different locations and many different wells that we're working with, and we work with very complicated geology. And we have to figure out how to correlate across from one well to another, given these signals. What we found is that we can use knowledge, information about depositional systems. We can teach them to deep learning, machine learning methodologies. And when we combine them together with methodologies like dynamic time warping that I just showed, we can do an exceptional job of mapping across space. This is essential to the stewardship of the subsurface, understanding how we're connected from one location to another. And machine learning is providing excellent opportunities to incorporate our geoscience knowledge, engineering knowledge, and to build efficient workflows. The results are we have improved quality of estimation as far as how to connect up what's going on in the subsurface and then how to best mitigate risks or to improve recoveries to better use the subsurface in a safe and environmental manner. All right, let's talk about garbage in, garbage out, bias in, bias out. This is fascinating because many of us have heard this before. If you work in modeling, you've heard the whole garbage in, garbage out statement. We are concerned with bias. It turns out that many, in fact, let me stop there. I would say most subsurface data sets are intrinsically biased. And what we did is I challenged one of my PhD students, Wendy Luo, go and prove that, quantify that the data sets are biased and prove that that bias, or show it. Let's find out that that bias impacts the estimates from machine learning. And what was fascinating was that we actually found when we looked at a variety of different models, here's one where we don't account for bias, and here's one where we account for bias, it would change the estimates we would make across a different series of inputs. And if you look carefully, you'll see changes between these maps indicating different predictions. Now, we can quantify this. We can look at a variety of ranges of bias in spatial data. And we can find out, in fact, that this does result in bias in machine learning. We published this paper. This was amazing. People had not been thinking about this. And we found a methodology by which we could dramatically decrease that bias, a weighted, spatially weighted machine learning approach. And we're looking at applying that to a variety of different machine learning approaches. I think this will be a very important moving forward. There's all kinds of opportunities to improve our ways to address bias. A well-known methodology in spatial data analytics and geostatistics is cell-based declustering. Mabadege was actually working in the area of how can we make these methods of bias removal in our models objective. They were relying on a subjective choice of scale, a cell size for the cell-based declustering method. What was fascinating is that she realized that we could use objective spatial statistics like Ripley-Kay's function, a spatial statistic, to come up with an optimum scale to apply our declustering technologies. This is a perfect example of spatial data analytics being used to improve our debiasing of data sets in the subsurface. Fascinating, with a significant improvement, reduction in the error. It was really, really great. Now, anomalies are impactful. Spatial anomalies, how do we find them? How do we detect them? Wendy Luo, once again, has actually developed a new technology by which, and we just recently published on this, by which we can go through spatial data sets and we can detect anomalous connections, anomalous rates of change. Now, this is important for any of you. We already said we have big data. Working with this big data, this is a wonderful opportunity to be able to find those locations to focus professional time. Are those data that are erroneous? Are they locations where the geology, the subsurface has changed? Did we get the model wrong? These are all great opportunities. We need to be able to parse through and learn from our data. Spatial anomaly, spatial temporal anomaly detection are all essential. Now, what's very interesting, if anybody here works in the subsurface, I imagine many do, you often have this problem. You get data, you get new data, you compare them, it changed, it's different. But if I can quote an old supervisor from Chevron, we need the difference that makes a difference. What's really impactful? We've developed a new concept of geostatistical significance. Take this example right here. You drill a single pad from which you want to produce a resource. You drill another pad. What we're able to do now is we can make comparisons in any feature, any spatial feature across these pads, and we can ask the question, are they significantly different? Is this truly a better location? Is there a trend? All of these essential problems can be addressed objectively with geostatistical significance. This is data analytics now accounting for the spatial context. Very, very exciting. Spatial continuity is essential. Anyone who works in the subsurface knows that that's at the heart of making spatial predictions. We often use the varogram model. Can machine learning assist with that? This is fascinating. A lot of time is spent on building varogram models, in fact. And so what we've been able to do is we use deep learning. We can take an existing spatial data set, and using a technology known as convolutional neural nets, we can actually map that directly into a full exhaustive spatial model and then map with another convolutional neural net to the spatial continuity parameters. This directly impacts spatial prediction with great accuracy. Is it accurate? Well, here's a cross plot right here, cross validation. If you look at the actual estimates versus the true values, you see in general, we do a great job at making these estimates of the spatial continuity direction and the range parameters. Really, really interesting. Great things that we can do under the hood now and locally to assess or understand the subsurface. Well, many of us work in fractures. Fractures are important. Fractures have a huge impact in the subsurface and reliability of anything we try to do with subsurface resources. Can we quantify those? We partnered with the Bureau of Economic Geology with the FRAC Consortium, and we've developed novel methodologies to be able to quantify fractures locally, globally, across a profile. We can now understand if things are having specific cluster patterns or if they're anti-cluster type patterns. This is huge to understanding what's going on with the potential of subsurface production in the presence of fractures. We've even invented really cool methodologies to be able to simulate specific fracture patterns to account for what we call in the science data imputation. Now, in the geoscience area, this would be the issue of part of the outcrop was obscured by vegetation or other types of obstructions, and we can impute the missing parts of our data set. This is very important in the subsurface where many of our data sets have gaps. Machine learning requires good training models and what I should say, good geoscience input. Our team has been working on a wide variety of different technologies so that we're able to integrate in knowledge about the specific patterns of the subsurface coming from geoscience expertise, outcrops, full numerical simulations, flume experiments, high resolution seismic. We're able to now build very realistic models of the subsurface. What's very powerful about this? Well, number one, we can train deep learning to build advanced models and workflows, but we can incorporate all of the available geoscience information as we build these. What's awesome about these models is we can build 10 million cell models in a fraction of a second and build thousands of those and explore uncertainty spaces. In fact, we can take those models as a learning laboratory about the subsurface to explore uncertainty. And here's an example right here from one of my senior PhD students, Honggong Zhou, where from this suite of models, from his methodology for training model generation, was able to identify the most important components of the subsurface for early, middle, and late production schemes. This is a fascinating opportunity. This is excellent. We can learn so much more. But let's not stop there. Let's build the subsurface models with deep learning. Here's an example right here. Now, clearly, I have crossed the line into trying to baffle. I'm not trying to baffle. I'm just showing the idea that any component of subsurface modeling can be attacked with deep learning. Here's an example of well-based conditioning using image inpainting. Stratigraphic profile, you can incorporate any type of fractures or faulting or any type of discontinuities using conditional GAN, generative adversarial networks, and history matching can now be accomplished using generator and discriminator technologies combined with ensemble Kalman filtering. It's fascinating. We can now start to explore these uncertainty spaces so much better. Now, what's really important is if we're going to build a wide set of models and try to say we're representing an uncertainty space, we need to test that. And here's an example right here, a truth model and realizations trained over time with deep learning and with the new methods we've developed. And if you look at it, if you look at the uncertainty space projected to a low dimensional, two-dimensional space, you can see that the models that come out as we improve the training start to span the entire space of uncertainty from the geologic inputs. This is a great model validation, and in fact, it goes further than that. We know in subsurface modeling that our models are not truly hierarchical or multi-scale. In fact, we use a methodology known as the cookie cutter approach. We model at different scales and we put things together. What's amazing now with these new methodologies in deep learning is we can now build models that truly honor the relationships across all scales to improve decision making. All right. I know I'm having too much fun. I'm going to just finish up with a couple of interesting additional topics and then give a summary. Flow forecasting is essential in our business. Anyone who works in that knows that with improved computational efficiency of the models and computing resources, it's been balanced out by more complexity, more physics, bigger models. And so it still takes too long to flow. What we've done is we've started to develop flow surrogate models using deep learning. Here's an example right here where we can predict the fluid flow velocities with high accuracy, intergranular. This is a model that's 2 centimeters by 2 centimeters. We can predict fluid flow at that scale within a fraction of a second. And what's amazing is that this is the first step, the true multi-scale flow forecasting, where we can now account for the important geoscience information with regard to those pore structures. Here's an example where we trained with that previous model. It was using just a sphere pack model, very simple. And we were still able to apply it to real rock samples, tomography used in order to get a full three-dimensional mapping of it. And even though we have cementation and complicated grain geometries, the accuracy of these models is unbelievable. It really is showing us that we can use deep learning and generalize and for a wide variety of different problems. Exciting stuff. Okay, I won't talk anymore about flow surrogate modeling. We have a lot going on here. Well, I can't help myself. Eduardo Maldonado has been doing an exceptional job of working and moving forward with convolutional neural networks to now make predictions through time and space of important spatial features like saturations and pressures at high resolution. This is really, really important to be able to make flow forecasts. And he's demonstrated that even though he trains on a model, he can actually show great accuracy when he has dissimilarity. This measure right here is telling us about the dissimilarity between the models. You can see there's some degradation of accuracy, but there's still persistence. It still does perform in a robust manner as we change the models up. Okay, let me go ahead. I'm going to summarize and end with a couple of concluding remarks. I hope I've convinced you that the subsurface is unique. I hope I've convinced you that there's a digital revolution that's impacting all fields of our economy. And I hope I can convince you that engineers and geoscientists are well positioned to learn these new technologies and add value. There's new digital solutions for the subsurface, data analytics and machine learning, and there's great opportunities to add value through new capabilities. Efficiency and automation, engineers having to have more time to do engineering. Maximize the value of data, find new patterns, focus on what matters. Assistant modeling, real-time feedback to learn while you're modeling. That to me is very exciting. I would love the subsurface to be just like TurboTax. You put in your information at the beginning of TurboTax, you get an estimate of your return, and every time you put new information in, you see the impact. That's how this could be. Every time we make a subsurface choice, we see the impact on the decision criteria and the decision. New improved models, step change, better integration of all expert knowledge, all data sources. We can build new digital skills for new opportunities for engineers. All right, thank you very much.
Wow, thank you, Michael. That's a lot to digest in a short amount of time, but a great overview. Thanks.
Thank you.
Just want to remind the people on the webinar that if you have questions, type them in the Q&A box, and A couple of them have come in, so let me jump on those. One is, and I'll start with a foundational one, and it comes back to the beginning of the talk. So where specifically the question is, how does this relate to data mining that's been around for a long time, right? And I think, you know, if we look at data mining as kind of informational for machine learning and model generating, and ML taking it next level. Can you touch on that?
That's a great question, Dr. Rowe. I do appreciate that. When I talk about the fourth paradigm, data-driven science, I feel a little bit like we could move that date back. And because I've worked with many people who are working in machine learning, and they say, oh, this is the fourth wave of machine learning technologies. And I do recognize data mining, kind of the original approach using inferential statistics to try to learn patterns from complicated, varied, massive, multivariate data sets. I would agree. In fact, I'm very embracing. When I look across the different technologies and statistics and machine learning, probability, and so forth, I put it all together. I think we need to learn from, in fact, what's very interesting is many of our approaches that we use nowadays are really, they've been used in those areas: principal components analysis, clustering analysis, all the variety of different ways we can do cluster analysis with complicated varied data sets like density-based clustering and so forth. All of these technologies are continuing on. And so I see this all basically fitting together, Dr. Rowe.
Fantastic. One other point about industry-wide collaboration and modeling. So if you look at what's happening in the technology space, right? I think Microsoft, Amazon, and Facebook have Onyx, right? That open neural network exchange, and they use that shared data to enhance deep learning models. Is that happening in the energy and petroleum industry?
Yeah, and that's a great question. If you look, so first comment I'll make is that energy does have great research. I've seen many cases in which research within companies is cutting edge, where research inside of companies are really pushing the science forward. So I give them full credit for that. I also acknowledge the fact that I've seen a transition. Even since the time that I first joined the University of Texas at Austin, I remember visiting companies and I was opening up Jupyter Notebooks, I was using GitHub, and there was almost a bit of a shock. What is all of this? Now, I taught recently, just last week, at one of the super majors, and I'll tell you what, they're rolling out their new tools, they're using open source, they're talking about contributing back to open source. Of course, there are examples of multi-company collaborations around subsurface modeling that could be discussed too. I'm seeing a major transition in our business where they're recognizing the value of contributing back to open source.
Fantastic. Canavis is sending me a message. I just want to take a quick look at it. At one point, you mentioned domain knowledge is still most critical. This person asked, as a young subsurface engineer, relatively a novice in both subsurface knowledge and data science knowledge, would you say it's actually more important to develop subsurface knowledge before deep diving into digitization?
Yeah, and that's a great question. From my perspective, well, first and foremost, you know, the amazing thing about being an engineer is that there's so many great things that we can do. It is a wonderful, fundamental, educational approach that allows us to go into so many different fields. At the same time, what I have observed for what I would call the data scientists within our field is I've seen a strong focus on the domain expertise, then building up and adding coding capabilities. And now when I talk about that, I did do full stack development in C++. I do not wish that upon you. Those were dark days in my office of trying to find some type of memory leak and so forth. Like that is a different path. I mean, focused on workflows to get the job done. What I found with coding, I've switched. I do mostly Python now. I don't do a lot in C++. I code much less and I get a lot more done. I'm harnessing the world's brilliance. And so I feel good, practical, solid skills within Python would be exceptional and it's accessible to the average engineer. Math and statistics. And this might be my bias, but I think every engineer should have a strong math and statistics background already. I think that that's fundamental to what we do. Why? Well, the math, I don't even have to say it. We know that. But when it comes to statistics, I think we all recognize for every engineering analysis, we need to deal with uncertainties. And so we should already have that, and that should be something that's on our journey. So I would really say focus on the engineering path, add in knowledge or experience with working with the methodologies, the codes, the workflows, the algorithms within machine learning data analytics. I think that's a very powerful route to follow.
Great. And then a kind of a two-parter, a little bit related. How are chemical engineers positioned to and using ML in the oil and gas industry versus kind of the geoscience side we've been talking about?
Yep. And you've seen I have a bit of a bias. I come at it from the subsurface. What's really, really interesting is that in the last couple of years, I'm starting to get chemical engineers in my undergraduate and graduate courses. Data analytics, geostatistics, machine learning. They're learning it. And I'm hearing really good feedback from them. Now, this is how I would compare and contrast. The area of chemical engineering at times can have denser data. For sure, they may not be in the circumstance where they're sampling 1/1,000,000th of the system directly like we may be in the subsurface. At the same time, they have similar problems, complicated, high-dimensional problems, fundamental engineering physics that needs to be incorporated. And so from my experience, and actually when I ran my subsurface machine learning graduate course last term, I had one of my chemical engineering graduate students in the course actually did a special research project. I had a chance to review and look at that. I see huge opportunities to add value on that side too.
Yeah, I think that flows into a question here specifically about applying this approach to biodiversity, water data, urban geospatial software. Yeah. So I think for me that aligns exactly with what you're saying about the chemical engineering side.
Yeah. Can I jump in with a couple more points around that?
Yeah, please.
I actually have one of my PhD students working on groundwater for the state of Texas to help us protect that important resource for the state and for the people of the state. And we recently just formed a partnership working directly with and in collaboration with the IC² group here on campus, which to me is just awesome because now we get to combine the whole thing together. Talk about the resources, talk about the people, talk about how we can benefit communities in Texas. I agree. I think we'll find new patterns and it will help us make better decisions to assist these communities. I'm very excited about that opportunity.
And so kind of linking those pieces together, transfer learning is another really important part of machine learning. And so one thing that I know has been explored well in the oil and gas domain is transfer learning. Is your group working on that, or you seeing any good trends around that?
Yeah, we are working in that field. What's very interesting, what comes out of it is this whole issue about how do we update models? How do we incorporate new information into models? And fundamentally, to what degree do our machine learning models generalize? In other words, if we train in a set of data right here, can we use it to make predictions accurately in a setting, or maybe just marginally, just a little bit different? And to me, it's fascinating because we learn so much when we look at that. We're learning to what degree these models are useful. We're learning to what degree do specific features generalize while others may not. I think there's a lot of opportunities plus efficiencies because we're able to build models that can be used in a wide variety of applications. That's a huge opportunity to use knowledge from densely sampled settings in sparsely sampled settings. I'm excited with that. I have a couple of PhDs working in that field.
Well, excellent. I'm going to ask one more question, and then after that, please feel free to wrap up and give us your final comments, and then we'll hand over to Canavis. Carbon capture is a really important topic in industry right now. And so we have a question from Mitchell Johnson. Many oil and gas companies are now looking into CO2 sequestration concepts. How is the research in oil and gas withdrawal from the subsurface different from injection of CO2 into the subsurface, and how is this linking back to ML?
Yeah, and that's a great question. I would say that there's a lot of similarities. I would suggest that for the case of carbon dioxide sequestration, that we may be even more sensitive to fluid and rock heterogeneity, that we may be even more challenged to build realistic, accurate models and with realistic uncertainties. In fact, if you consider the types of assurances we need to give with regard to the period of time for sequestration, we really need to understand those uncertainties. And so what I would suggest is that ML, machine learning, offers unique advantages. In fact, I have a PhD in geostatistics. I can say I honestly wrote one of the major books in reservoir geostatistics. And I can stand in front of you right now and say that we are building models with realistic levels of heterogeneity, data integration that we could never do before with geostatistics. And so I think this will be a critical part of the solution for CO2 sequestration.
Fantastic. Any closing comments for us?
Well, first of all, thank you very much for this time and this opportunity to present. I hope this was useful to the people who are listening. I am optimistic. I have confidence, and it comes from teaching many working professionals, many engineers and geoscientists, and I've seen them in periods of weeks, learning new skills, adding new value, and gaining new confidence in the digital revolution. So I'm just excited. I'm really excited about this, and I'm grateful to be able to share this. Thank you.
Fantastic. Thank you. Canavis?
Well, thank you so much, Dr. Perch, and hello, everyone. My name is Canavis Smith, and I want to formally thank each of you for joining today's webinar, and we hope the conversation was valuable. Next, we wanted to highlight a few of our professional development short courses and future webinars. As you've heard today, lifelong learning and technical adaptability is fundamental in preparing individuals to remain competitive in today's workforce. If you enjoyed our fantastic speaker, you can learn more from him in our graduate certificate program. Texas Engineering is now offering a 100% online petroleum engineering graduate certificate in data analytics, specifically built for the oil and gas industry. The certificate is a graduate level coursework that receives transcript credit for each engineers in this field. Both of these graduate level certificates that you see on the screen are created for degree seeking and non-degree seeking students to provide them the tools to optimize processes and systems that you use every day. Visit our website today to learn more about our simple application process. Next, we wanted to highlight some of our upcoming skills-related courses with the pipeline technology and energy fundamentals. If you or your organization need additional training in this area, please contact our PTEX department today. Next, we also want to thank the 3 units of the Cockrell School of Engineering that helped put this wonderful program together. First is our Texas Engineering Executive Education Program, who works to reskill and upskill companies' current workforce, either through our master's degree programs, graduate certificates, or short courses. So if you have a need around STEM education or training, make sure to contact our department to learn more. Next is our PTEX department, or the Petroleum Extension of Texas. This department has been around for over 75 years, serving the oil and gas professionals with skills training, either through e-learning, publications, online, or in-person training. We have the training to meet your oil and gas needs. And last but not least is our research relations team. This team partners with industries to solve some of the world's biggest problems in energy, water, and transportation, and many more. The Office of Research Relations works to facilitate and derive high value from research collaborations between companies and UT's researchers. If your company would like to partner with the university to explore additional research opportunities, please email the Research Relations Office to initiate a discovery discussion. All 3 units are here to serve you and your company through education, training, and research. So feel free to contact us at any time, and we would love to collaborate on helping you reach your company's full potential. As we continue in our Text Talk series, I wanted to make sure you are aware of our upcoming webinar. On February 26th, Dr. Joan Brunecki will be discussing CO2 capture with ionic liquids. And on March 12th, Steve Hodges will be sharing his thoughts on offshore floating production systems. We hope each of you join us for future webinars, so mark your calendars today. If you would like to provide feedback on today's webinar or to learn more about receiving CEUs for today's talk, make sure to complete the evaluation survey in your email following this presentation. Once again, we'd like to thank you for joining us today. We hope you have a great weekend, stay safe, and hook 'em horns.